Well, everyone, we are up for the next talk, and after having a quite virtualized morning today, we continue with virtualization procedures in general. Today with us is Michael Steil. He's the founder of the Linux Xbox project, and he's already spoken at some previous congresses, so you might know him. Well, virtualization in terms of VMware are around since 1999, and up to today we've only got VMware, Microsoft Virtual PC, and one, I think, Russian competitor. Now, the question is why 7 years of development only produced 3 software products. That has to do with some severe problems you've got to do when you virtualize computers. And Michael is going to give us some introduction about these problems and how to possibly solve them. Enjoy. And one thing, we're already a little bit behind of time, so please keep your questions for the end, so not to disturb the speech too much. Thanks.
Closer, so? Oh, now it's, yeah. Oh, it's louder now. Okay. Okay, so yeah, I'm Michael Steil. I've done Xbox hacking and all that, but that's not so interesting anymore. So I figured the entrance fee is too high for me, so I had to give a talk and had to prepare something. So I speak about VMware because that's some of my interest anyway. It's not only VMware; it's also Parallels. It's also Virtual PC. But I think everyone knows the term VMware, so that was probably the best way to find a title. So what I'm going to talk about is why virtualization is interesting to us at all. Of course, virtualization is a nice hack. Many people use it. But the point is, why would you want to understand it? Are there some hacks involved? And the answer is yes. What would you want to know about virtualization? For all this, I have planned in some time about operating system basics, for all of you that don't know them. Then I'll talk about OS virtualization, why x86 is so broken, and how Intel and AMD have fixed that in the last generation of their products. First, let me tell you that I am not a VMware employee or anything, and all the information that I have comes from their open source code, because they have kernel modules that have to be open source because of Linux, or some other projects that are open source anyway, like Mac on Linux or QVM86 of QEMU. So let's look a bit at the history of virtualization products that we had in the past. VMware is the big thing. It has been existing since 1998. It was some startup company, and still today is the #1 for virtualization. Also on the market is Virtual PC. It has been found, some guy named Eric Trout has founded Connectix. He's very well known because he did the first commercially successful dynamic recompiler, DR, for AirPool for the 86K to PowerPC transition. And now Virtual PC is owned by Microsoft. Also, there is a company, or there's a product called 2on2 from some Russian company, which works great with OS2. There's also Svista from some Russian company, which works great with OS2. There's also a product called Parallels from Russia. Funny things go on there. There's Plex 86. You might know the Box project by Kevin Lawton, who did this single-handedly himself. But the Plex 86 system, well, it failed. It never could run anything. But there's QEMU by another genius, Fabrice Bellard, who you might know of products like RZexe from the 80s. Or he also held the record of calculating pi to I don't know how many digits some years ago. And he also did QEMU. So virtualization seems to be some magic thing by some unknown startup companies, by some geniuses bought by Microsoft or some weird Russian companies. Those can do it, tend to write the same application 3 times, yeah. But my point is virtualization is something quite old. Old like this. This is an IBM System 360. And it has some tape drives here. What this system can do is about the same as this. Yeah, I had to find an excuse to put a C64 in my slides. I have to do that all the time now. These systems could do virtualization, maybe not virtualization as you know it, but the problem was, maybe you already know where this is going, that if a CPU is executing some code and it has to read from tape, it cannot execute any more code while it's waiting for a tape. So it has to execute, wait, execute. So in order to speed all this up or to make better use of the very expensive 1.33 megahertz CPU, you could do this. You could attach a second tape drive, and while the CPU was waiting, or one process was waiting for the tape drive, another process could just continue executing. And when it was waiting for the tape drive, the other one could execute again. So the more tape drives you added with this system, the better the CPU usage would get. Oh, and this is called multitasking. Maybe you know about it. Maybe you use it. But this is virtualization, because you virtualize your system. And this is all important for our virtualization term that we have today. So what it looked like was, in DOS times you had hardware and you had one single process, like a DOS application, with its hardware interface. And with an operating system, you have hardware, and the operating system with its hardware interface is sitting on top of that, providing virtual hardware interfaces to its processes, and several processes sitting on top of that, each with its own hardware interface to the virtual hardware. These processes are completely separated, as if they were running on a virtual machine. And they have their own virtual time. They all think they're running alone and have all the time, and their own RAM and their own I/O, basically. So that this separation works, we need two modes of operation for the CPU: supervisor mode, which has full control of the machine, and user mode for everything that cannot directly control the machine, but every time it wants to do that, it has to go through some code in supervisor mode, which is done using a trap, for example, the scheduler, which schedules between the different threads of execution or processes. Every time a system call, which is a virtualized I/O access, is done, and also access violations go from user mode to supervisor mode. Let's look at a timeline how scheduling works in this. This is all very trivial, but these are the basics to understand virtualization, because then it gets really complex. One process is running and it gets interrupted by a timer interrupt. Then the system switches to the scheduler, which will then decide what process to run next. In this example, process 2, which will be halted by a timer interrupt again. Scheduler, another process, this time process 1 again. Time interrupt, scheduler, process, and so on. This is called a time slice, the time of execution that one process has. And as you see, the system switches between user mode and supervisor mode all the time. The scheduler is a part of the operating system and runs in supervisor mode, and only it has full control of the hardware and can therefore switch between threads and all that. User mode cannot do this. So this is virtualization of time. We have to virtualize memory just as well. Every process has also the full system, has the full memory in theory, because it's virtualized. We have we have several processes, each with its unique address space of the full 4 gigabytes, for example. But we only have one physical memory. So what we could do is to have a base address and a limit address and just map big blocks into physical memory. But a better idea is to, as you can see here, to map every, for example, 4 kilobyte page of any address space to physical memory. And some pages are just not mapped, you cannot access them. And also for the second process, so this is a lot more flexible. Now, virtualization is like an operating system of an operating system, because virtualization can, or virtualization as we call it today, can virtualize operating systems and not processes, so it is nested virtualization. While so far we had hardware and the operating system with its hardware interface on top of that, and the processes running on top of the operating system, with virtualization we have the virtual machine monitor with its hardware interface sitting on the raw hardware, providing virtual hardware. So this is the same picture as before so far, because we just have another level of virtualization. And what sits on top of the virtual hardware is this time not the processes, but complete operating systems with their hardware interface again. These processes, these operating systems have their processes running in them, and these operating systems cannot interfere with each other if the hypervisor doesn't want to allow that. So processes ran in user mode, and let's say they still run in user mode. Operating systems run in supervisor mode. But so what does the virtual machine monitor run in? Supervisor mode already has the complete control of the system, typically. So let's introduce a third mode, a hypervisor mode. Okay, this is just another excuse to have the German flag there. I admit it. But with three modes, there's no way that supervisor mode can have full control of the hardware. Of course, only one system can have full control of the hardware, only this can make it secure. So hypervisor mode is privileged mode, and the others are not privileged. So if something in user mode does something that user mode shouldn't do, it will trap. For example, the scheduler, if the time slice has come to an end, if a syscall is made to kernel mode, page faults and access violation will trap from user mode into supervisor mode. And also supervisor mode will trap for mostly the same events into hypervisor mode. For scheduling between the operating systems and not the processes anymore, the operating system. Also page tables, I/O accesses, or if the whole operating system crashes, then hypervisor mode will just deallocate the operating system but not crash the whole machine. So hypervisor mode, as I said, is privileged, the only privileged code on the system, and both user mode and previously supervisor mode, or well, it's still called supervisor mode or kernel mode now, must then be unprivileged. But what's the difference between user mode and supervisor mode if both cannot have full control of the system? Therefore, we could simplify the whole system and just call all this user mode, or just run all this in user mode and run all this in supervisor mode. So virtualization doesn't need three different modes of execution on a CPU. 2 modes are always enough, but 3 modes can be an optimization. Now let's have a look at how the different parts of the system interact here. If we only have two modes of execution. With 3 modes of execution, the last slide told you that user mode will talk to kernel mode and kernel mode can talk to supervisor mode. But if we only have 2 modes of execution, it gets a bit more complicated. So in supervisor mode, there runs the virtual machine monitor with its hardware interface to the real hardware. And in user mode, we have the OS, which should normally run in kernel mode, but we now run it in user mode. The user mode has its hardware interface, which connects to the virtual hardware of the virtual machine monitor. And all the communication between the operating system and the hypervisor is done as on a 3-layer system. Any scheduler, page table, I/O accesses or crashes will be just communicated to the virtual hardware interface of the VMM. But what about all these? Oh, that slide is on the wrong page. Anyway, what this slide is going to say, this slide is supposed to be telling you how these traps work. For example, this is a real-world example of instructions that will trap, that